Okay, we're going to talk about differentiability, which we will be able to abbreviate. So remember, we can abbreviate things. We don't need to stress out over being able to spell them correctly, but we do need to know what they are and be able to use them correctly, okay? So if you recall, when we were talking about continuity, there was a continuity question where it said the function is differentiable. And at that point, you were supposed to write continuous above it, right? Because that's like, we didn't know what it was. So now we know that means we can take the derivative. But here's the key here. Differentiability implies continuity, which means if it's differentiable, it has to be continuous. But continuity does not imply differentiability, or it doesn't guarantee it. Okay, just because it's continuous doesn't mean it's differentiable. It could be, but we don't know. But if it's differentiable, it's definitely continuous. Okay, so that's one of those things where it can kind of get confusing how you say it, so make sure we can keep that straight. All right, so so what this is saying is if a function is differentiable at a point, then it is continuous at that point, has to be. The converse, so flashback to geometry when you had converse, inverse, and contrapositive, that means saying it the opposite way. The converse is false. A continuous function may fail, bless you, to be differentiable at a point in its domain. Okay, so here's an example, and I'll show you why as soon as we understand it a little bit better. But an example would be that, let's see, f of x equals the absolute value of x. So would you agree you know what that parent function looks like? It's the v, right? Okay, so it is continuous, but not differentiable. So I'm going to abbreviate continuous and differentiable, right? I mean, you can write out the whole word if you want, but it's continuous but not differentiable at x equals 0. Okay, and so some of the wording, some of you, and more than one of you have said like when x equals 0 and when x equals 3, that sort of thing. We can say when a equals 1 and when a equals 2, but at x, remember x and y, it gives you a location, it's a point. So it's important that if you're going to talk about x, you say at x. So if it helps to make you do the little at sign instead of writing at, that's fine. Like you can do that. That's what that little blob is at x equals 0. Maybe it's better for you to write the word. But make sure when we're talking about x that we're saying at. Okay, we can say when a equals 0, but at x equals 0, that sort of thing. All right, so we'll talk about why it's not differentiable in just a minute. So here's in other words, if a function is differentiable at x equals c, so if it is differentiable, it must be continuous. Okay, keywords here, must and may, those kinds of things. However, if it is continuous, it may or may not be differentiable. So it could be, but we don't know for sure. And if a function is not continuous, then it is definitely not differentiable. Because those two, they do go hand in hand. So if f is not differentiable, one of the following is true. So these are the things that make it fail to be differentiable. If it's not continuous, okay? If it's not continuous, it's not differentiable. If the limit, now this right here, the limit as x approaches c of this kind of thing, right? We looked at this briefly the other day, but in the definition of a derivative, we had this alternate definition. So instead of looking for the equation, this was the alternate definition. So the derivative of f at a point x equals a is given by this. So this is the derivative, all right? So when we look at this, and the derivative gives me what? What does the derivative tell me? The slope at a point, right? It's an instantaneous rate of change. So this tells me that this right here is f prime, okay? That is what this is referring to. This limit is the derivative. So if the derivative from the left or the slope from the left is not the same as the slope from the right, so the derivative from the left is not equal to the derivative from the right. And we'll look at that from a graph in just a second. Okay. And that means the slope. Okay. Or if f has a vertical tangent at x equals c. So we're going to consider the graph of f below, which consists of 2 semicircles and 2 line segments. So if you look at these two semicircles here. Right? We've got a vertical tangent right here. So remember our tangent lines, so I'm going to use my, like if I drew in a tangent line right here, that slope would be 0, right? And then my slope gets steeper and steeper and steeper. To right here at 2, it would be a vertical line. So this tangent line would be vertical. Can you find the slope of a vertical line? No, it's undefined, right? So if I can't find the slope of the tangent line, I can't find the derivative. Does that make sense to you? Plus what's happening is, so if this is 0, right, then this is my slope. Would this slope be positive or negative? Negative. Okay, and the negative number is getting smaller and smaller and smaller, right? It's getting steeper, which means like the value is getting bigger, like it'll go from 2 to 3 to 4 to 5. But when it's negative, that number is actually getting smaller, right? So this is getting smaller and smaller and smaller and reaching negative infinity, and we can't actually have a slope of negative infinity. Okay, so that's why that vertical tangent doesn't work there. Okay, and that's what this says right here. At x equals 2, so it's differentiable at all x in the open interval except at x equals 2, because we have this vertical tangent right here. Vertical tangent. Then at 4, it's not, because it's not continuous, because I have a jump. So then x equals 4, because it is discontinuous. So this is discont. Then this one says it's not differentiable at x equals 5. Well, look, this is x equals 5 right here at this point. It's not differentiable at that point. It's continuous at that point, but it's because these limits don't exist. And what do these limits represent? The slope at the point, right? And this slope, at any of these points, the slope's the same because it's a piece of a line, right? So this slope right here, slope equals 1, and this slope equals negative 1. So as I approach 5 from the left, the slope is 1. As I approach it from the right, the slope is negative 1. So since they're not the same, it's not differentiable. But it would be differentiable here. What's the difference between here and here? The shape of the graph. This is smooth and curvy. This is pointy, right? So you can't come to a point. Everything's nice and curvy, we're fine. It comes to a point, that's bad. So this is what we would call a, we can call this a sharp turn. Turn. Oh my gosh, I still can't freaking word. Turn, which is also called a cusp. It's okay if we don't remember that word. We can just talk about sharp turns. Okay? We don't want to say pointy, but that's what you want to think of. It's not a curve at that point. It's a sharp turn or a cusp. Okay? We good with that? What questions we got? Okay. Beautiful. All right, so flip it over. So this kind of repeats the same thing. We talked about something being differentiable, a derivative, specifically that a function is differentiable at a value x if the derivative of that function at that point exists. If we can take the derivative, it's differentiable. This implies there are points which are non-differentiable, okay? Which is kind of what we just looked at. Some of this repeats a little bit. Here are some examples. So it says use the graph of each function, then the graph of each function, the definition of the derivative, and the fact that a derivative is a limit to determine why the functions below are non-differentiable at the given points. Okay, so we have this little graph here. Why are you touching your phone? Okay. Well, your phone is on your paper. What are you doing? Okay, look. What kind of transformation is this? What happens? Just if we're going to graph this picture. Graph this graph. Moves to the right 2. So it's going to look something like this. This is at 2. Okay? So is it differentiable at 2? No. Why? Because it's pointy, but we would say sharp turn, but yes. Okay, so, and that's true, but we're going to use, it says use the graph of each function, the definition of the derivative. So we're going to do this, okay? And because of that, we know that our slopes aren't the same, Okay, and it's not the slope of the line, it's the slope of the tangent line, but because they're lines, it ends up kind of being the same. So what we want to write is this. And this is the, let's see, let me write it up here. Okay, this is the alternate definition of a derivative. Okay? And remember, the actual definition of the derivative is a limit. So f prime of a is equal to the limit as x approaches a of f of x minus f of a over x minus a. So that gives it to you at a point. If we're talking, and we know what our point is x equals 2. We're not having to do the x plus h stuff here. Okay? So when I go and use that right here, I can see that the limit as x approaches a, not a, 2, because we know what 2 is, I'm sorry, approaches 2 of f of x minus f of a, which is 2, good Lord, f of 2 over x minus 2. Okay? So that limit, I have to do it from the left and the right. So that limit, I'm making that from the left. The slope coming from the left does not equal the limit as x approaches 2 from the right of f of x minus f of 2 over x minus 2. Okay, so there's my statement. The limits are not the same. Therefore, f is not, now I don't want to just say f is not differentiable, because it is. It's just not differentiable at x equals 2. Okay? We okay with that? And now, this is the official way, which I wanted you to write it at least once, because we're going to see some multiple choice where you have to recognize that. And I know it was written on the front, but I needed you to write it. Moving forward, we can talk about the fact that we have a sharp turn or a cusp, which I don't know if that's actually written in there somewhere. Okay, we good? All right. Let's look at this one. So this one also just gets shifted to the right. We have a horizontal asymptote at y equals 0 because it's bottom heavy. And then I'm going to have a vertical asymptote at 2. And my graph looks like this. Okay. So I want to know at 2. And we're looking at the slope, not the limit of this function, the limit, the derivative, the limit of the derivative, okay? So even though, yeah, I can see that the limit is different, that's not what we're looking at. We're looking at the slope of this. So as I approach from the left, the slope, here's my tangent line, right? My tangent line starts to go like this, which would approach negative infinity, right? And my slope goes like this, which is also approaching negative infinity. So they're approaching the same thing, but it's negative infinity. It's one of those that does not exist. Instead of having to really overthink that and really worry about how all that works, what we're going to learn about differentiability, or what we just looked at, is we know this is not differentiable. Why? What were the 3 things we had to have? Because, well, we don't have a tangent line, but we do have a vertical asymptote. So is this continuous? It's discontinuous. Can it be differentiable if it's discontinuous? Nope. So I can say f is not continuous at x equals 2. Therefore, f is not differentiable at x equals 2. Okay. Kind of broke the rules there because it said to use a limit and stuff, but that makes you have to think about that slope, which makes your brain hurt a little bit, and it's not necessary. Okay, so here are 3 more functions that are not differentiable, and we're not going to write out the slope stuff. We're just going to talk about why they're not differentiable. So this one, x minus 1 to the 1/3 power at x equals 1. Why is it not it's differentiable here, 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 and here, but why not here? Is that an asymptote? Tangent. Be careful, because they kind of, I mean, both of them would work to say no, but that's a vertical tangent line. Okay, so we would say not differentiable due to vertical tangent. Not differentiable at x equals 1 due to vertical tangent at x equals 1. Okay, we good with that? All right. What about this next one? The differentiable at x equals 1? Is it differentiable at x equals 2? Yes, but not at x equals 1. So it's not that the function overall isn't, is it at a point. So we can say not differentiable at x equals 1 due to what? A cusp, okay? We can say cusp, or you can say sharp turn if you don't remember the word. Sharp turn at x equals 1. Sometimes you might feel like you're repeating yourself about locations, but it's okay. I mean, it's better to say it more than once as long as you're correct than to say it up here when you really needed to say it down here. Does that make sense? All right. So then, last one. Is this differentiable at x equals 2? No. Okay, so think about this. If it's differentiable, that means I'm going to get the slope at a point, right? I can't get the slope at a point if there's not a point there. Right? That's why it has to be continuous. So I can say not differentiable at x equals 2 due to, I don't know why all of a sudden I'm saying due to, you can say because, I mean you can say this different ways, due to point discontinuity at x equals 2. Okay. We good? All right, so we have a definition of differentiability. A function is differentiable at, I should say, all values of x equals c if it has to be continuous at c, has no sharp turn or cusp. I knew that was written somewhere. So the left limit doesn't equal the right limit. And f of x doesn't have an asymptote or vertical tangent line. Right? So continuous, no sharp turn, no vertical asymptote or vertical tangent line. We good? Those are the pieces there. All right, and once again, differentiability implies continuity. But continuity does not imply differentiable. But it has to be continuous to be differentiable, and sometimes that's easier to check. So if it's differentiable, then it must be continuous. If it's continuous, it may or may not be differentiable. This is the same thing it says on the front because I copied and pasted a couple of different things. But if a function is not continuous, then it is not differentiable. Here's another little notation issue here. It's also worth noting that differentiability and continuity can both be described over an interval. Okay, continuity is usually defined on a closed interval, and differentiability on an open interval. Okay? And we'll look at kind of what we mean by that in just a second also. Okay, we good so far? All right. All right, so it says for the two graphs, oh, no, I guess I need to give you that piece of paper. Huh? Okay. So for the two graphs below, list the x values for which function is not continuous and explain why it's not continuous, and then not differentiable and explain why. All right, so let's do number 1. So A. A says where it's not continuous. Where is this function not continuous? 3. X equals 3. So I'm going to say not continuous at x equals 3 because of what? Vertical asymptote. Okay, we agree with that? All right, where is this function not differentiable? The same point. So not differentiable at x equals 3 because why? Good, because it's good. So I can say because not continuous or discontinuous is fine. Because not continuous at x equals 3. On my paper, I actually have it written backwards. I wrote, I should say, here, we're going to add something in here. This is my bad notation. So f is not continuous at x equals 3 because of vertical asymptote, and f is not, that says f is, not differentiable at x equals 3 because f is not continuous. So you have to say what you're talking about. Like there's no it, and I didn't have a. So f is not continuous at x equals 3 because of the vertical asymptote. So what I actually have in my paper is that f is not continuous at x equals 3, therefore f is not differentiable at x equals 3, which is the same thing. It's just said backwards, right? Okay, try number 2. So what you get written down for A and B on number 2. Okay, so I'm going to write some stuff down. My words will most likely not be exactly what your words are, and that's okay. It doesn't mean that you're wrong. Don't scratch yours out or erase it, because you gotta take your own thoughts and put them on paper and make sure they make sense, right? So, is there any discontinuity? I can't even say it. No. So I would say f is continuous for all x. Okay? How else could I say that? All values of x, beautiful. We're okay. Anybody have anything different or not sure if what they have is right? Okay. And see, so that, here's what drives me crazy right now is that I don't always know for sure if that would be 100% acceptable or not. You know what I mean? Those are things I keep having to go ask other people. But because like right here, f is continuous until it gets to here, right? So it's kind of important to add for all values of x, just to add that. But I don't know that that would necessarily be wrong. Because I do know what you mean with that, and I think it's kind of okay. But, you know, it's one of those things where my opinion really doesn't matter. Got to make sure I know that I can answer those questions, but I'll check on that. All right, so what about differentiability? Is it differentiable everywhere? At some places. Where is it not? -3 and 3. So I could say f is, and again, don't erase yours if it's not exactly this. This is what's coming out of my head right now. F is not differentiable at x equals, I'm going to put plus or minus 3. If you listed them separate, that's totally fine. Okay? Because that's what y'all just told me. It's not differentiable. So that's what I write down with those places. And I would say because f has sharp turns at x equals plus or minus 3. Now, the official answer would be that the limits from each side of f prime of x don't equal each other. You could use the word cusp, something like that. Okay? Do we all have something that would sort of match that, even if our wording is different? Yes. Devin, are you falling asleep over there? No. We're just really studying your... Yeah. No, I would say or, though, instead of and. Well, I don't know. And is probably fine, too. It's not differentiable here or here and here. I guess it's the same either way. Yeah, that's fine. No, as long as you said at, and if you're you're basically listing them at that point, so you're fine. Yeah, and you don't have to put them together. I just did, so. Good question. Anything else? Okay. So let's look at piecewise here. It says when dealing with continuity and differentiability of piecewise functions, we need to examine the x value where the rule changes, okay, just like we did for continuity, right? In order for a piecewise function to be continuous where the rule changes, remember that it's like x equals c, so here it would be x equals 2. The limit from the left has to equal the limit from the right, which has to equal the point, right? So for continuity, the point exists, the limit exists, the point and the limit are equal, right? Those are the three pieces there that we have to have. In order for a piecewise function to be differentiable at x equals c, the function must be continuous at the limits of the derivative. Okay? So we're going to have to use both. So it says determine if it is continuous and or differentiable. So we're using continuity, which we've already done. We're just going to have to go through the continuity piece of this, and then we go and see if it's differentiable, okay, without looking at a picture. So here's how we do continuity. We start with the point, f of 2. F of 2, I would substitute it in here, right? So I get 2 squared minus 6 times 2 plus 10. So that's 4 minus 12, negative 8 plus 10, 2. Do you agree with that? Yeah, it's 2. Okay, so there's 3 parts to continuity, right? This is the first part. The point exists. Boom. The second part is the limit exists from both sides. So I have to do the limit of f of x as x approaches 2 from the left, and the limit of f of x as x approaches 2 from the right. So from the left would be this one. It would be 4 minus 2, which is 2. From the right, it would be this one, which we already found, and that is 2. Okay? So since the limit from the left and the limit from the right exists, that tells me here then that the limit itself exists. The limit is x approaches 2 of f of x equals 2, like the limit overall. The point exists, the limit exists. My third thing is that the limit and the point are equal. So the limit as x approaches 2 of f of x is equal to f of 2, which is equal to 2. Since I've shown all 3 parts, what does that mean? It's continuous. So I can say therefore, like all of this stuff is my explanation, right? This is some of the words that some of y'all were having trouble with. I've got all that. I've used the rule for continuity. So I can say therefore, f is continuous, and I can't just say continuous. It's continuous at x equals 2. Okay, so I've got my continuity piece. Because the question says we are going to determine if it is continuous and or differentiable. Just because it's continuous, does that mean it's differentiable? No. Okay, so in order for me to figure that out, I have to find f prime of x. So I'm going to take the derivative of a piecewise function, which is pretty simple, right? So this, I'm just using my power rule. So the derivative of that first piece is going to be 2x, then minus 6. What's the derivative of 10? 0. And then watch this. I'm putting x is greater than 2. I don't know that it's greater than or equal to. I know that's what this says, but right now it's greater than 2 until we find out some other information. Then I take the derivative of 4 minus x. What's the derivative of 4 minus x? Negative 1. And this is when x is less than 2. Okay, everybody good so far? So now I have to see if the limit coming from the left of the derivative is the same as the limit coming from the right, because these are my slopes, right? So I have the limit of f prime of x as x approaches 2 from the left, and the limit of f prime of x as x approaches 2 from the right. So notice your test for continuity and your test for differentiability, it's the same process, just one uses f and one uses f prime. Okay? So this is equal to, so coming from the left, what do I get? Negative 1. Coming from the right, I get 2 times 2 minus 6, which is negative 2. Okay, so my limit from the left does not equal the limit from the right. So I can say the limit as x approaches 2 from the left of f prime, make sure you're using the right notation, of x does not equal the limit as x approaches 2 from the right of f prime of x. Therefore, f is not differentiable at what? X equals 2. And notice when you actually have to do some work, that's kind of when the therefore makes sense, makes more sense maybe, depending on how the words are coming out of your head. Sometimes if I'm just writing my explanation, I end up putting this part first and then explaining myself, but like your explanation is your work. Okay? We good with that so far? Any questions? Ask me questions. Please, y'all are comfortable enough with me and each other to actually ask, right? Okay. All right, so we check for continuity and then differentiability every time. All right, so now we're going to look at a couple of questions of what this would look like on the AP exam. We're going to work a couple together, and then I'm going to have y'all work some. Because this is what it would actually look like on the exam. All right. Okay, so here's where you got to pay attention to what things say. What is given to you graphically and algebraically. It is asking you, it says if f is the function defined above, then f prime of 2 is blank. Do I get to take 2 and just substitute it in here? No, it's asking me for f prime. It's not asking me for f of 2. Okay, so there's a lot of times where you'll be given f and you're asked about f prime, or you're given f prime and you're asked about f, and you got to be able to know how to go back and forth. Now, this isn't just about finding the derivative here. This is, I have to know if it is even differentiable. So we always check continuity first. Okay, check continuity first. You have to check that. So to check the continuity, because if it's not continuous, then it's not differentiable, right? So that means I'm going to find f of 2. What's f of 2? Negative 4 times 2 plus 3. Right? Negative 5. Yes? Okay. And then I need to find the limit as x approaches 2 from the left of f of x, and the limit as x approaches 2 from the right of f of x. So from the left would be this one right here. So I'm going to get negative and then 2 squared plus 1. So it's negative 3. And then from the right, it's going to be negative 4 times 2 plus 3, which is still negative 5. Okay. So is this function continuous? No. So the function is not continuous. If it's not continuous, and this is a multiple choice question, so I wouldn't have to write out the rest, like I could write out my explanation, but this is not continuous. We can at least write this. Not continuous. If it's not continuous, can it be differentiable? No. So what's my answer? D. But check this out. If I just took the derivative, okay, here's why we don't get this part here. If I just took the derivative, f prime of x is equal to, okay, so that's going to give me what? Negative 4 when x is greater than 2. Not greater than, I just said that. Greater than 2. And it is negative 2x when x is less than 2. If I had just taken the derivative and moved this sign over here, what would you think your answer is? Negative 4. That's going to be a very common wrong answer because you're going to see derivative and you're going to be like, oh, let me just take the derivative and I'll plug it in. And you would get this answer, and that's a big fat no. You would get that answer if you missed this part because this is how it has to stay because it's not continuous. If it's continuous, then I can put that little thing in there. Okay? That's why you have to check continuity first. We're not just making you do extra work. I do. What do I write? What do I write for it? Let's see. I didn't check my, okay, I'm going to write this down. Didn't check my continuity. Didn't check continuity first. Ooh, I know. These have been on my, so I'm writing it down so I don't remember, so I won't forget. Yeah, you don't go to calculus prison. All right, we good? Let's see. Why don't we skip number 2 for right now? And y'all do number 4. Number 4. It's asking you if it's continuous and differentiable or one or the other, or what is it? So what are you going to have to check? Everything, right? Oh. Good. And don't get sloppy just because it's multiple choice. Like as you're now if you're taking the actual test and you see stuff, you wouldn't necessarily have to finish it off so that you know, for time, but it's best to keep going with your notation to make sure that we can get this right. So we get We'll go back and do those other two on another day. Maybe, maybe not, just depends. But here's your assignment. I know you got a lot of yellow papers today, but I also don't want things to be super tiny for you. Okay, let me know if you have questions on this. We still got a couple minutes if you do. Yes? Where do I get the negative 2x from? Oh, because I had to take the derivative. This is f prime. I took the derivative of this. Yeah. Yes, ma'am. Okay.